Well, thank you. And let me start by taking a closer look at why people are so excited about machine learning and AI more generally. So recently, we've all heard about the great successes of AI. So of course, there was DeepMind's AlphaGo. And with progress in medical applications, some people now also claim that AI will replace doctors earlier than we think. However, I want to start with an example, well, that first explains why people are so excited, but then I'll also show you an example why people are maybe a little bit too excited. So first here we see an example of such an AI application. So that is an image classification system from Clarify, which is a company that offers image classification as a commercial service. So on their website, they have this demo where you can upload an image, and then it will spit out probabilities for what is shown in the image. So it is a little bit small, but what you can see here is we upload this image of a cow, and then indeed the most likely label we get says cow, followed by other relevant concepts such as pasture, grass, etc. And so with these performance, some people in the AI community are very optimistic. So for instance, Ilya Sutskever has said a few years ago at NIPS, anything a human can do in a fraction of a second, a deep network can do too. But now let me go back in time for a little bit to 1904, and let me show you about, tell you about Clever Hans. So Clever Hans was a horse that was set to perform arithmetic tasks. So its owner would ask Hans, for instance, what is 3 + 1? And then Hans would answer by tapping his hoof. And well, as you can imagine, this raised a lot of public interest. And there was, in fact, like a formal commission. So the German Board of Education appointed this commission to investigate the case, which then concluded, as you can see here, that the horse actually reasons. However, after a few years later, the psychologist Oskar Pfunks investigated the case a bit more, and he actually showed that the horse was making use of the unintentional minimal movements of its questioner. So what was happening is that as the horse was tapping, the questioner's posture and facial expression changed in ways that were consistent with an increase in tension, which was then released when the horse made the final correct tap. And that in turn provided a cue for the horse so it that it could use to stop tapping. So no, the Clever Hans did not really reason. But why am I telling you all of this? So going back to 2019, this story should remind us a little bit to be cautious when we judge the capabilities of the current methods. So let's look at another image. So this time we see, again, a cow, but it's on a beach. So maybe in a little bit unusual location. We ask again for the probabilities. And now this time, in none of these predictions, we see the cow. So it starts with beach, water, and sea, but it doesn't see the cow, which is clearly visible in this image. So now the system doesn't seem so smart any longer. And what is happening here is that this image comes from a distribution that is somewhat different from what was used when training the system. So presumably, the training data didn't contain any cows and beaches, or just very few. So we have a distribution shift between test time and training time. And while this is not so surprising when you think about this problem for a little bit, and it's nonetheless quite concerning, given that systems of this type will be used in safety-critical environments sooner rather than later, but their robustness properties are not very well understood yet. So judging the statement in this slide, I think we can be a bit more skeptical about this. So the work I will present now was exactly motivated by this sort of behavior. So we were interested in developing a method that has some robustness property with respect to certain kinds of distribution shifts between test time and training time. And this is joint work with Nikolai Meinshausen. So the example I will look at now for the rest of the talk is the following. So we have images of people, well, mainly face images. And what we want to predict now is whether the person in the image is wearing glasses or not. And here you can see the data, or a sample from the data we have available at training time. And now the standard thing would be to do, we want to minimize the expected loss for some suitable loss function. And then what we do in practice, we optimize the empirical counterpart of this objective, and maybe we add some complexity penalty, like an L2 or ridge penalty for the weights. So let's see what we get for our data set. We train with just this standard objective. We get a training error of 0% and then a test error on our test set of 2%. So everything looks great. And now, sometimes in the future, we receive data of this form. So again, I'm showing you a few observations from the data we get in the future at production time. So it doesn't seem so different from the data I trained on, so I apply my system. But actually, this time, we suffer from a test error of 65%. So let us understand a bit better what is going on here. And so what we did in this work, we casted this problem of image classification in terms of a causal graphical model. And if you're not familiar with kind of sort of causal reasoning, I think the gist of what I'm going to present can also be understood as if you just read this as a plain graphical model. So we try to model and conceptualize the data generating process. So let me go through the nodes we see in this graph. So we have y, which is the class label, and then we have images x. And in our case now, so the images, in a sense, are recordings of y. So in our causal graph, they come after y, so they are descendants of y. And that's why we say that the prediction is anti-causal, because we sort of predict against in the other direction rather than the causal one. OK. And then after we train our system, here we get this y hat. These three nodes are observed. Everything else is latent and unobserved, but it helps to understand these distribution changes we're interested in. So up here we have the domain, which you can think of as the place of observation where the data was collected. And here it is latent in the sense that at training time, we only have access to data from one domain. But we do expect in the future that certain aspects of our distributions will change in different domains. And then we say the causal effect from y on x is mediated via two types of latent features. So there are the so-called core features, x core, and the style features. So the core features are the ones that are really inherent to the object of interest, while the style features are more things like background, brightness, image quality. So these are things that can change. And we model this difference between the two by allowing these external interventions delta on the style features, but not on the core features. And so this represents that if in future domains these deltas have different distributions, then the distribution of the style conditional on the class label can change, while we say that the distribution of these core features conditional on weight, that remains invariant. OK, so in terms of our example, let's understand what's going on in terms of core and style features. So here we could say the core features are the presence or absence of the glasses in the image. So conceptually, it's very close to the label y that we want to predict, but it doesn't have to be exactly the same. And now in this example, actually, the style turned out to be image quality. So what was happening here is that the data we had access to at training time, for people wearing glasses, the image quality was on average lower than for people not wearing glasses. So in other words, image quality was very predictive for the class label y. However, we were not aware of this. So had we been aware of this, we could have maybe tried to correct for this. But it wasn't really obvious from looking at these images that we had this bias in the data set. And then at test time, what happened, like we were so unlucky that actually now image quality was lower for people not wearing glasses than for people wearing glasses. So in other words, that relation had kind of flipped adversarially. And now this explains the error rates I was showing you that we were doing so poorly on this future test data set. Okay, so now our motivation is to be exactly robust to these sorts of domain shifts that arise through these changes in the distribution of the style features. And now when we think of our neural network, what we need to ensure is that we need to learn a representation which only uses these core features, but ignores the style features. But since we only input kind of the pixel values, it is not immediately obvious how you would achieve sort of this behavior. And what we exploit here in this case is that sometimes you have a certain group structure in the data. So in case of our example, we have several images of the same person. So these are the ones you can see here that have these red borders. And then, so in other words, these groups arise through a conditioning on Y and this identity variable that we'll call ID. So for example, here on the right, you can see two images of the same person and the same class label. And this gives us what I'll call a group in the following. And the nice thing is we only need this additional information for some points in our data set, but not for all of them. So here in our model, we now add this ID variable to the graph. And we model the difference within a group as arising through a difference in this delta. So if you look at, again, at this guy on the right, we say the core features here are the same, but, well, the image is still different. And this difference arises through this delta. And now the key idea will be that we want to exploit the constancy within a group, but we want to penalize the features that change within a group. So let me connect this to the notion of distributional robustness. So we want to perform well under arbitrarily strong interventions on the style features. So that means, in terms of our example, no matter how much the image quality in test distributions is different from what we observed during training, we still want to be able to classify whether the person is wearing glasses or not. And so this goal is represented in this objective, in this adversarial loss. And now we have an objective that actually says we want to perform well on a whole class of distributions, namely all the ones that arise through these interventions on the style features. So this is a form of distributional robust inference where we define the class of distributions we want to perform well on in terms of a causal model and a specific set of interventions we want to protect against. However, these are not known explicitly, so now the question is, how do we optimize this objective? So what we can do now is to exploit this group structure in the data. So remember that I was saying that the group differs up to a difference in delta. And the key idea is that we need the classifier that we learn to be constant as a function of delta. So what we can do now, we use what we call the conditional variance of the prediction. So that is what we see here. So this conditioning on the Y and ID gives us images of the same person. Then we see what are the predictions we get for the same person. And we want these to be the same or very similar. So that's why we compute the variance over these. We do that for all groups. And then we want this term to be small. So then in practice, we use this penalized objective. And we add this conditional variance penalty just to the plain loss function, which, say, minimizes the cross-entropy loss. And then lastly, let me show you how this performs on the example I was showing you. So here again, we see the training data and then the test data set that has the same distribution as the training data. So here you can see the numbers I was showing you before, the 0% and the 2% of the convolutional neural network that doesn't do any special regularization. And then in the line below that, you can see this added core penalty, that stands for conditional variance regularization, where we see that in these distributions we do a little bit worse. And that is because we do not rely on this predictive value of image quality. So we force sort of the network to ignore this predictive feature in these distributions. But now when we go to the second test data set where this relation between image quality and Y has flipped, we do much better with the core penalty, even though we also suffer from a higher loss. So to conclude, we've seen that biases in data sets can yield very undesired features inside of deep neural networks. And exploiting additional information such as the grouping structure and causal reasoning increases the robustness of predictions. And with that, I would like to thank you for your attention.
Thank you. I have a question regarding the types of data. So did you try to use the similar algorithm for any other use cases than image quality?
So we've mainly looked at image classification, and I think in that setting it's quite relevant because the input features you give, like there you cannot do any sort of feature selection as opposed to a setting where your features have really a semantic meaning. We have looked at simpler cases, kind of where we don't have images, but rather simulated data to also test it. But we haven't looked, for instance, at like kind of natural language settings or anything, which would be very interesting to explore. Yeah.
And in terms of images, is there some other parameter apart from image quality that comes to your mind that could also influence in
So
this?
we've looked at a number of things. I mean, kind of to kind of demonstrate that this kind of method works, we've looked at different things like brightness, image quality. Then you can also look at cases where you have a discrete style features. So for instance, we looked at cases where you want to predict gender, but now you have a confounding that like women would be more likely to wear glasses than men, and then you want to kind of get rid of this nuisance and this confounding. So these are sort of the settings we've explored. Yeah.
Thanks.
I just have a quick question on image quality. So it's not resolution, obviously, no? As
No.
the resolution has to be the same. So
Yeah.
what do I have to imagine if I look at quality or be aware of?
So we just, like in this case, since it was a proof of concept, we artificially kind of blurred the images to some extent. But don't, like the exact procedure, I don't recall what it did exactly to the image, but it was essentially like some effect like that. But the resolution in the end is the same, yes.
So most learning algorithms always start from the input data. What if instead of like kind of completely getting rid of like the naive input and only taking like kind of inherent features into account, like I compute structure information of my image, like kind of like distances or whatever, or like I'm able to quantify some structural characteristics. Can I like make my predictions robuster by like only predicting or only like inferring results from structural or image inherent features?
So I'm not sure I entirely understood the question. So are you saying that if you do some sort of pre-processing step where you extract features and whether you would classify on those, whether then things would be different?
Yes.
So I think if really like you manage to capture like this bias in a certain way, and then you apply the same method, I think it would be equivalent. But otherwise, it would still be hard to get rid of this fact. I mean, the style feature here, the image quality, is very predictive for Y. So in any sort of feature selection algorithm, if you just want to optimize predictive accuracy, it would always be beneficial to rely on this. So you need to have like some sort of mechanism that really forces the network not to use this information that is really useful for the objective we give it. So that's why I think it's certainly like if you do some sort of pre-processing, maybe these things would come out in a way, but those features would still be predictive. So that's kind of the
yeah, or kind of having like a neural network, but always a fixed pre-processing layer of like kind of like first extracting, like kind of having like some important sampling or like kind of.
Yeah, but again, then you still have to somehow make sure it doesn't use this really useful bit of information that is good for the objective at training time.
Thanks.
Yeah.